What specific challenges in the existing AI training paradigms does the OML 1.0 protocol address, and why is it important to have both community ownership and control?
The OML 1.0 protocol addresses specific challenges in existing AI training paradigms, particularly the issues of ownership verification and usage accountability. It introduces a three-party system involving the community, model hosts, and provers to ensure that model usage is tracked, and that any violations of the agreement can lead to penalties for the host. This is crucial because it prevents unauthorized fine-tuning and ensures that the model remains aligned with community values. Furthermore, community ownership is essential for verifying the lineage of models and ensuring that all inferences are accounted for, while community control is necessary to embed deterministic functions that guarantee the model behaves predictably according to the community's values. Together, these components foster a robust framework that protects against misuse and misalignment, ultimately enhancing the integrity and loyalty of AI models.
Can you explain how the OML 1.0 protocol operates step by step, specifically focusing on model lineage verification and usage accounting?
The OML 1.0 protocol operates through a structured process involving model lineage verification and usage accounting. First, every model released on the sentient platform is embedded with unique lineage fingerprints, which are pairs of key response that authenticate the model's identity even after fine-tuning. When a model is accessed, the host must sign an agreement to use the OMList model, which includes stipulations for usage and alignment with community values. For usage accounting, the host must obtain a cryptographically signed permission string, sigma Q, from the sentient platform for each query made to the model. Provers, acting as benign users, can verify the model's usage by checking if the host has the permission string, and if the output matches the expected response based on the fingerprints, ensuring that any violation of the agreement can be detected and penalized. This dual mechanism of lineage verification and usage tracking ensures both community ownership and alignment are maintained.
Provide a concrete example of how model fingerprinting works within the OML 1.0 protocol. Walk us through a scenario of a query being processed and how ownership is verified.
In the OML 1.0 protocol, model fingerprinting is utilized to authenticate ownership and track usage of community-owned models. For instance, when a host wants to use an OMList model, they first sign an agreement and receive access to the model, which includes embedded fingerprints in the form of key response pairs. When the host processes a query, they send it to the sentient platform to obtain a cryptographically signed permission string, sigma Q. A prover, acting as a benign user, can then issue a special query, ~Q, which corresponds to a fingerprint key. The response, ~R, generated by the model is sent back to the sentient platform along with the key response pair, ~Q~R \closing parenthesis dot. The verifiers check if the host has the permission string, sigma ~Q, and if the output, ~R, matches the expected output from the OMList model, confirming ownership and ensuring compliance with the usage agreement. If any discrepancies arise, the protocol can enforce penalties on the host for violating the terms of the agreement.
What empirical results were obtained in implementing the OML 1.0 protocol, particularly concerning fault tolerance and adherence to community values?
The implementation of the OML 1.0 protocol demonstrated significant empirical results in terms of fault tolerance and adherence to community values. Specifically, the protocol's design, which includes a three-party system involving the community, model hosts, and provers, effectively tracked model usage and ensured compliance with community agreements. This tracking mechanism allowed for the detection of violations, such as unauthorized fine-tuning, which could lead to monetary penalties for non-compliant hosts. Additionally, the protocol's fingerprinting technique provided robust authentication of model lineage, ensuring that any changes to the model could be traced back to the community's original values. Overall, the OML 1.0 protocol not only maintained high performance, but also reinforced the alignment of the model with the community's core values, as evidenced by the successful tracking and penalization of any deviations from agreed-upon standards.
Discuss the trade-offs between decentralization and Byzantine fault tolerance in the proposed method. How does your approach manage these trade-offs, particularly in the context of community governance?
The proposed method highlights a critical trade-off between decentralization and Byzantine fault tolerance, BFT. While decentralization allows community members to suggest any data point for consideration, BFT requires mechanisms to prevent malicious data insertion or Sybil attacks, which can compromise the integrity of the model. To manage these trade-offs, the approach suggests using proof-of-stake solutions, which can implement either a decentralized staked filtering mechanism or a staked data submission mechanism with possible challenges. This ensures that while the community retains governance over the model, the integrity and security of the data used for training are upheld. Ultimately, the method aims to create a balance where community ownership and governance are preserved without sacrificing the robustness required for BFT, thus fostering a secure and participatory environment for model evolution.
What are the limitations or potential vulnerabilities of the OML 1.0 protocol and the proposed community alignment method, especially in light of adversarial attacks?
The OML 1.0 protocol faces limitations primarily related to its reliance on community trust and the potential for adversarial attacks. While it aims to ensure compliance through a signed agreement and the threat of penalties for violations, rogue hosts may still attempt to fine-tune models to misalign them with community values, exploiting the semi-open access nature of the protocol. Additionally, the protocol's effectiveness hinges on the ability of provers to accurately verify model usage and ownership, which could be compromised if adversaries find ways to bypass the verification steps. The community alignment method, while designed to maintain model loyalty, is vulnerable to both white box attacks, where adversaries fine-tune the model, and black box attacks, where adversaries use prompts to elicit misaligned responses. These vulnerabilities highlight the need for robust defenses against fine-tuning and prompting attacks, as well as the importance of maintaining the secrecy of fingerprinting functions to prevent adversaries from easily circumventing the model's protections.